Are you done copying?
Yes.
No, please.
No or yes?
No,
Okay. So an object moves around in a circle of radius 3 meters with an angular velocity of 4 radians per second. Calculate I, the frequency, I, the period of rotation, and I, the speed. Okay, so let's see how we can solve this question. Solution. Let's extract the information given to us. The question has provided the radius of the circle. R is equal to 3 meters. We have the angular velocity, omega, is given as 4 radians per second. So these are the information we have. We are to first find the frequency. So how do we get the frequency? Yes, the first question is to find the frequency. Class, how do we determine the frequency? Quick one within a minute. In a minute, yeah, we have to respond to this. Anybody?
Mr. Teacher,
Nanajua.
the angular velocity is equal to 2 pi f.
Good.
So frequency will be equal to the angular velocity over 2 pi.
So since angular velocity is 2 pi f, then making frequency the subject, we have omega on 2 pi. Thank you. And so omega is provided 4. The angular velocity is provided. And so the frequency would be 2 on pi. And what is 2 divided by pi? Yes. What is 2 divided by pi? Quick one. Hey, you are quiet too. Gloria and Co.
Mr. please, did you say find 2 over pi?
Yes. What is 2 divided by pi? So approximately.
Mr. please, 0.636.
So 0.637 hertz is the frequency. Avia Pokua, help me find the second question. We are to determine the period. How do we determine the period? Avia? Avia, I'm waiting for you. Yes.
Mr. Just join a few minutes ago. Please, could you move the camera up so that I could look at the session? Thank you very much.
Avia. Okay, maybe Avia is looking for a calculator. So let's have Eliana to tell us how we can determine the period. Eliana.
Please, period is equal to 1 over f.
Good. So a period is equal to 1 on frequency. Evie, are you there? One over f. And so once we have the frequency, we just substitute.
Mr. Lee, are you talking to me?
Efia Pukua. Not Efia Champon. Your time will come. Okay. So Akofala, I hope you are true.
Yes, please.
Okay. So please divide 1 by 0.637. And what's the final answer? What's your final answer? Oh, hurry
Mr.
up.
Edia, 1.5698.
Give it to me in 3 decimal place. 1.5.
Then it will be 1.57.
Second. All right. Then the last question. We are to determine the speed. The speed. How do we determine the speed? Gloria, how can we calculate for the speed? Gloria, dear. Glory.
Mr. Edia,
How do you find the speed?
Mr. Edia, please. Please, speed or velocity is equal to angular velocity times the radius.
Okay. I guess
And
this is
velocity.
I guess this is a BBI, it's not Gloria.
Hey, I'm so sorry. I thought it was me.
Oh no, that's fine. That's fine. Gloria can have another question. So V is equal to, okay, radius times angular velocity. And we have the radius, we have the angular velocity. So it's a substitution thing, okay? And this establishes the relationship between linear velocity and angular velocity. So radius is 3, angular velocity is 4. So meaning that when these quantities, radius and then angular velocity, are not given in SI units, you have to convert it to SI units before you can express the speed in meter per second. So 12 meter per second is the speed. Please, are we okay? Are we okay?
Yes, please.
Okay, second question. And I'm reading. Are you ready? Class, are you ready?
Yes. Yes, please.
Okay, so what is the angular acceleration? What is the angular acceleration What is the angular acceleration of an object in a circular path of radius of an object? The angular acceleration of an object in a circular path of radius 15 meter with a linear acceleration of 16 meter per second squared. What is the angular acceleration of an object in a circular path of radius 15 meter with a linear acceleration of 16 meter per second squared? That is A. B. Hello.
An object in a circular path
Of radius 15 meter with a linear acceleration of 16 meter per second squared. With a linear acceleration of 16 meter per second squared. Then B.
16.
16.
Thank you.
Then B. B. The rim of a compact disc. The rim, RIM, the rim of a compact disc starts from rest. The rim starts from rest, and after 30 seconds, and after 30 seconds attains an angular velocity, and after 30 seconds attains an angular velocity of 6.6 revolution rev 6.6 rev per second. 6.6 rev per second.
Please,
Mr.
can you
Dia.
repeat it again?
The rim of a compact disc. The rim of a compact disc. Rim, R-I-M, of a compact disc. Start from rest. And after 30 seconds, attains an angular velocity of 6.6 revolution per second. Attains an angular velocity of 6.6 rev per second. Calculate the angular acceleration during the time interval. Calculate the angular acceleration during the time interval. So I want you to think through the first question. Look at the first question. Just solve the first question.
Please, can you take a shot?
Can I?
Take a picture.
Of the question?
Yes, please.
Yeah, no. So just attempt the first question. Roma, are you there?
Yes, please.
And you are quiet like that. Okay, so Eliana. Eliana,
Prestigia,
I've sent you.
thank you.
Efiapoko, I hope your phone is not off. Or your battery is gone. Once Efia is not responding, then the phone is not alive. So just attempt the first question. Efia Kutu, what did you get as the answer for the first part? What have you had? Efia Kutu,
Please, I'm not done.
you have to you have to finish. If you are true, can you share your answer with us? If you are true solving the I part, can you share your answer with us? Whoever is ready. Okay, so what is the angular acceleration of an object in a circular path of radius 15 meter with a linear acceleration of 16 meter per second squared? So the linear acceleration A is given as 16 meter per second squared. The radius is given as 15 meter, and we are asked to find the angular acceleration. Don't forget, as the object's speed, linear velocity changes with time. An object is in circular motion. Okay, there's the center, there's the radius. Once the displacement changes with time, we have velocity. If the velocity is also changing, and the change of velocity is such that it is increasing as the fan. Okay, that's similar to the fan. When you start the fan, its speed will be slow. As time goes on, you realize that the speed will be increasing. So when the speed is increasing with time, we have velocity. So we have linear velocity within the circumference. Once there's a change in the linear velocity, there is also a change in the angular velocity at the center. All angular measurements, all angular quantities takes place at the center. So when this is changing, when the speed is changing, it means the angular velocity is also changing. And so a change in linear velocity gives us a linear acceleration. A change in angular velocity at the center gives us angular acceleration. And we derive the relationship between linear acceleration and angular acceleration. And this is how we derived it. If V is equal to R omega, when the velocity is changing within the circumference, delta divided by T, then the angular velocity will also be changing at the center. So with time, so this divided by T. This is giving us linear acceleration within the circumference. And this is also giving us angular acceleration at the center, alpha. And this is what we derive as the relationship between linear acceleration and angular acceleration. So once we have A, we have R, and we are asked to find alpha, you just make angular acceleration the subject, and that is A over R. Okay, A is equal to 16 meter per second squared divided by the radius is given as 15. So this is 1 point, yes, 16 on 15, 1 point.
1.067.
Okay. 1.07. And what's the unit? What's the unit? What's the SI unit?
Rad per second squared.
If you are saying it, you have to, if you are saying it, it has to be radian. When you are writing it, rad, R-A-D, Kezia, okay? So radian per second squared. When you are saying it, it is radian. When you are writing it, it's rad. So know what to say, what to pronounce when you are saying it, and then what to write when you are, there's the need for you to write. Then the second question, please, is it okay to all of us? Is it okay?
Yes, please.
Okay. The second question.
Mr. Dia.
Hello.
Mr. Dia, please, is it necessary to draw in, let's say, an exam?
No, I just gave you a sketch to explain further. Okay.
Yes, please.
The linear velocity, all linear measurements, linear displacement, linear velocity, linear acceleration occurs within the circumference. All angular measurements, angular displacement, angular velocity or speed, angular acceleration occurs at the center of rotation axis. Okay, so take notes. All right. Then
Mr. Dia, please can you repeat that?
all linear quantities or measurements, linear velocity, linear displacement, linear velocity or linear speed, and linear acceleration occur within the circumference of the circle. The object is moving. So all linear measurements occurs within the circumference. And all angular measurement, angular displacement, angular speed, angular acceleration occur at the center of rotation, the axis. Okay, so if a fan is rotating, its linear displacement, its linear speed or velocity, and linear acceleration occur at the axis, at the circumference of the circle. Okay, now its angular measurement, such as its angular displacement, its angular speed, and its angular acceleration occur at the center of rotation, where the bar is around which the fan turns. All right. Can we continue? So
Yes, please.
there is a clear relationship between linear and angular. And we saw this last time, that just as we have linear displacement, we also have angular displacement. So I gave you a table of linear motion as against circular motion, or even rotational motion. We also have another similarity when it comes to equations. You see, we have three main equations of linear motion and uniformly accelerated motion. Okay, so linear as against angular in terms of the equation. So we have linear as against circular in terms of equations of motion. What is the first equation of motion? Yes. And uniformly accelerated motion. What's the first equation? Yes. If you are example, give me the first equation of linear motion, uniformly accelerated motion. The first equation. It starts with V is equal to
V is equal to U plus AT.
good. Where V represents
Velocity, final velocity.
good. U represents
Initial velocity.
A represents
Acceleration.
and T represents.
Time.
I thought you said T. T represents T. When it comes to circular motion, okay, yes, we also have angular, okay. This is linear velocity, final linear velocity, initial linear velocity. We also have final angular velocity, final W2, initial W1 is equal to initial angular velocity plus the linear acceleration. Here we are talking about angular acceleration times time. We don't have angular time. That is why, you see, the condition for this equations of linear motion are uniformly accelerated motion. That is why in circular motion, we are also talking about uniform circular motion. Okay, that's also the condition on which this one also holds. Now, what is the second equation of linear motion? Dromo, give me the second equation of linear motion.
S is equal to
S
UT plus
UT plus
half AT squared.
half AT squared. Thank you. Under circular motion, S will be what? Under circular motion, angular S will be equal to
Theta.
theta, angular displacement. So theta is equal to, this is initial velocity. So initial angular velocity T plus half angular acceleration times T squared. Okay, and then the final linear velocity. Anita, Roxanne, just rock this for me. The last equation of linear motion. Anita. Oh, Anita is not here. Okay. Irene, the final equation. Let's not waste time. Irene. She's going to eat. So V squared is equal to, let's join the hallelujah chorus. V squared is equal to
U squared
U squared
plus 2AS
plus 2AS.
Let's join the hallelujah chorus and the circular motion too. Yes.
Final velocity,
So
angular velocity, final
omega 2 squared is equal to, oh, let's join
omega 1 squared
omega 1 squared
plus 2 alpha
2 alpha times theta. Thank you. So that's a similarity and one aspect of the similarity and linear and circular motion. And those terminologies, the motion starts from rest. The motion comes to rest. Equally apply when it comes to circular motion. Okay, so let's start the second question. Start work. Based on the information you have, choose the appropriate equation to solve the problem. So start work. I'll attend to you in about 2 minutes time. The question is that the rim of a compact disk starts from rest and after 30 seconds attains an angular velocity of 6.6 rev per second. Calculate the angular acceleration during the time interval. And here, I want you to have your angular acceleration in radian per second squared. In radian per second squared. Or let me pin you this way. Find the angular acceleration in radian revolution per second squared and in radian per second squared. 2. In revolution per second squared and in radian per second squared. Are we okay? I'll be with you in 2 minutes time or so. Hurry up. Please roll call. Roll call. Today's attendance isn't impressive at all. I want a roll call. So come up. Whilst you solve the question, come up for me. So you are looking for the angular acceleration in rev per second squared and then in radian per second squared. Okay, so in a minute's time, I think the line would drop.